Hey guys, Dr. J here, and in this video we're going to review some basics of linear algebra, matrix and vectors, things like that. So this is kind of a prerequisite for our course on potential field theory and also for the course that we have on inverse theory. So just to begin with the basics, we can think of a number as a scalar. So maybe we have x. So maybe we have x is equal to 5 or something like that, right? So this is a scalar quantity. Now, as you probably are aware, a vector is a multi-dimensional number. So we can write a vector v, for example, as a set of numbers. Sometimes it'll just be two numbers. And the key thing about vectors is that they have both a direction and a magnitude, but they can also be multidimensional, however you say that word. So for example, a 2D vector would have two numbers in it. We can write it like this. We could add a third number and get a three-dimensional vector, and you can really keep going as long as you want, and we can even have infinite dimensional vectors. Now we can also have a matrix, and the way a matrix is going to work, it's like a two-dimensional vector, which is not really the correct thing to say, because as I just said, if you have two numbers in your vector, that's a 2D vector. But spatially, we write this out on the board like this. So now we have both rows and columns in our matrix. And I'm using letters here, but these letters just represent some numbers. So we could have a particular matrix, and we'll often use capital letters for our matrices and lowercase letters for vectors. And sometimes I'll use two lines underneath a letter to denote a matrix. And if I have a vector, then I might put a single line under that, and that'll be my vector. Sometimes you'll also see an arrow on top, and that can also denote a vector. So let me just write out an example matrix for us here. There we go. We call this a rows by columns matrix. So in this case, this is a 3-row by 3-column, so 3 by 3 matrix. And this matrix has certain properties. So in this case, this is a square matrix. It has the same number of rows as columns. I could add an additional row here. And so now I have a 4 by 3 matrix. We always say the number of rows first in the matrix. So 4 by 3, that means this matrix has 4 rows by 3 columns. This matrix has what's called a rank. And the rank of the matrix is the number of what we call linearly independent columns. We'll talk more about that in a different video. But we can do certain operations with matrices and vectors. So let's look at that. One of the things that we can do with matrices and vectors is we can add them together. So if I have one vector, and I want to add another vector, then I would just add the numbers that are in those two vectors. Pretty straightforward. So just adding the top numbers together to get the number in that last vector, and then adding the bottom numbers together. Now you'll notice, in order for this to work, that I need to have the same dimensionality of each vector. So I need to have like we call this a 2 by 1 vector, so there's 2 rows, 1 column in a vector. Here's a 2 by 1 vector. If I was to make this a 3 by 1 vector, now this doesn't work. Can't add those together. They're different dimensions, and so that dimensionality is important for the vector. So we can add vectors together. We can subtract vectors in the same exact way that we would add them. We would just subtract the corresponding numbers. What about multiplying? How does it work if we have two vectors and we want to multiply them together? Well, you can't multiply a vector in the way that you would multiply a scalar because there are multiple numbers. So we need to have a different definition. And the kind of corresponding way that I think about multiplying vectors is with a dot product. So we can say one vector dotted into another, and that's one way to define a kind of multiplication kind of thing for vectors. And that is going to be the following. So v1 dot v2 is going to be all the numbers in v1 multiplied by the corresponding numbers in V2, and then added up together. So if my V1 is 1, 2, and my V2 is 2, 2, then to take the dot product, I would multiply the top numbers and then add those to the product of the bottom numbers. And I would need to sum that up, so that's going to be 4 and 2 is 6. So V1 dot V2 is the number 6. Some rules for dot products. Obviously, the number of, or the dimensionality of the vectors, the number of values inside each vector has to be the same in order for the dot product to work. So just like with the adding and subtracting, we need to have the same dimensionality for our vectors. Now there's another way to write a dot product other than just using the dot, which is V1 transpose. I have a little tiny t right there that you can hopefully see. So V1 transpose times V2. This is how we would multiply two vectors together. This is really the definition of what a dot product is. And how this is going to work is we're going to write this product out like this. So hopefully you've noticed something different here. Instead of writing my vector as a column, I've written it now as a row. And that's what this transpose means. I'm going to take my columns and turn them into rows, or rows and turn them into columns, vice versa. And this works for matrices as well. So we would flip the matrix around the diagonal in order to get a transpose for a matrix. But anyway, here this is my transpose vector, and I'm going to now do the same operation as before. And this is important because it sets us up for doing matrix and vector multiplication. So what we're going to do is we're going to take the first number in our row and the first number in our column, multiply those together, and then add it to the second number in our row vector and the second number in our column. So we're multiplying these two, and then adding them together. And hopefully you can see that that's the same as what we had before. So 1 times 2 is 2, plus 2 times 2 is 4, that's 6. So we can write a dot product in this way, or we can write it in this way. Now, the nice thing here is that we can extend this to a matrix. So now instead of having a vector here, I'm going to write this as a matrix. So I have some matrix A, and it's going to have some rows and columns, and then I'm going to multiply that by a vector. And let me write out this matrix in a slightly different way. What I've done here is I've taken my matrix capital A, so this here is A, and I've written it as 3 row vectors. So my matrix might have 3 rows and 3 columns. Oh, and I should mention, so my vector has only 2 numbers in it, right? So we'll come back to that in a second. But let's just talk for a minute here about these rows. So these are, and maybe I should say transpose here. It's not that I'm transposing the rows in the matrix, but I'm just putting a little transpose there so that you know these are row vectors. I'm taking the first row in the matrix, call that A1 transpose, taking the second row in the matrix, call that A2 transpose, and the third row in the matrix, I'll call that A3 transpose. And then this is just a row vector. So I can take this row vector and multiply it by this column vector. This is just a normal vector. And that is a dot product between the first row of the matrix A and the vector V, V2 in this case. If I can do this, if the size works out, in other words, what do I need for this to be able to work? What I need is for the number of columns in the matrix A to be the same as the number of rows in the vector V2. So if this were a number, let's say that A1 transpose was, let's just say that was the same vector as my V1, well, then this can work just fine. I have 2 numbers in this vector, it's a row vector, and I can multiply that by the 2 numbers in V2, and I can calculate the dot product. Now, one thing you might have noticed is I've got 3 row vectors here, but I've only got 2 numbers in the columns. So this matrix would be a 3 row by 2 column matrix, or just a 3 by 2 matrix. And the other thing that you'll have noticed is that a dot product of a row vector with this vector will just give me 1 number, which means I'm going to just get one number as my solution. So here, this row vector times this vector is going to give me a number. I'll call that number, I'm already using A, so I'll call that number B. B, and I'll call it B1 for the first row in my solution vector. Now I just continue the process. I've got two more row vectors here. So I'll take this row vector and multiply it by this column vector. That's going to give me a number, one number. I'll call that B2. Right there. And then I'll have my last row vector times my same column vector in every case, and I'll call that B3. And so then maybe I call this is now a vector, and notice that it's a different shape than my vector V2. So this matrix is a 3 by 2 matrix, the way I've defined it just a moment ago. This, if I keep the same V2 that I've been using, that's a 2 by 1 column vector. So my matrix is 3 by 2, my vector is 2 by 1. Notice that the inner dimensions here are the same. And so when I do this matrix vector product, and I'm going to erase this up here now. So what have I done? I've done A times V2, it's a matrix vector product. That's going to give me, my solution is actually going to be the outer numbers of this matrix vector product. A 3 by 1 vector. And I can call this vector B. So A times V2 in this case is equal to B, where A is 3 by 2, 3 rows, 2 columns. V is 2 rows, and then B is 3 rows. And why does that happen? Because I take this row times this vector, and that's that number. This row times this vector, and that's that number. This row times that vector, and that's that number. And I'm saying times, but I really should be saying dot product. This row vector is dotted into V with V2. This row vector is dotted with V2. This row vector is dotted with V2. So in every case, I'm dotting the row of the matrix A with the column vector V2. This is how we can do matrix vector multiplication. We take the dot product of each row in the matrix, multiply it by the vector. Now, you notice I've written this as the matrix times the vector is equal to some other vector, B, which we can calculate by taking those dot products that I just mentioned. What if I tried to say V times A? Let's just do it real quick. Well, first of all, this is not going to work because this is not a row vector. This is a column vector. And in all the multiplication that we've done in the video so far, we've used row vectors. So at the very least, we would have to transpose this. So we would have V2 transpose times A. So we can turn this into a row vector. We always pre-multiply with a row vector. Now what have we got? We have a 2 by 1. Sorry. Try that again. 1 by 2. So this is a transposed vector. That would be 1 row and 2 columns, because V2 had 2 numbers in it. And just to remind us, I think V2 was 2, 2. I've been using V2 for this example. So just 2 numbers, 2, 2. So V2 transpose would be 1 by 2. So we take this, we transpose it. That would be 2, 2 side by side, so that would be a 1 by 2 vector. Then A, what was A? A was 3 by 2. Notice these inner dimensions are different. That means we can't do matrix vector multiplication. Well, there's 3 rows of A, we already knew that. And there's 2 columns, but we need there to be 2 rows in A. Remember we had those 3 rows? If we did this, tried to do this matrix vector multiplication, we would end up multiplying 2 numbers by 3 numbers over here. Not going to work. We need those vectors to be the same dimension so that that multiplication can work. Now we could do the transpose of A. If we did that, A becomes 2 by 3. And A doesn't become 2 by 3. A transpose is 2 by 3. Now we can do it. Something looks a little interesting here. So I've transposed V2, and then I'm multiplying it by A transpose, and look what we're getting. Your two inner dimensions are going to cancel out. So your vector that you get as an output is going to actually be 1 by 3. 1 row by 3 columns. It turns out this is going to be actually just the exact same thing. So we had A times B2 is equal to B, right? So it turns out that this quantity is going to equal B transpose. And the reason is because of an identity. If we take the transpose of this whole thing, and we take the transpose of that, then we end up with B2 transpose A transpose. So we reverse the order of the multiplication step when we do the transpose. And we transpose each one individually and reverse that order, and that is how that transpose of that product works out. This is an identity which might be helpful in the future. I'm not going to worry about memorizing a lot of identities in this class, but this is an identity which can be helpful sometimes. Transpose of a product is just the reverse order of the products transposed. And that gives us B transpose. So it turns out that this works just fine if we take the transpose of both. If we tried to take the transpose of just one and do this, not going to work. We can do the same thing with the product of two matrices. Very simple. By the way, we didn't go through the example of the two matrices, but basically in this case, just like we multiplied a matrix by a vector, we got a vector. So you would basically do that for each column of the matrix. You would take each column, you would treat it like a vector. You would multiply A times the first column of B, A times the second column of B, and that gives you your columns in your new matrix. So that means that the product of two matrices is another matrix. That also means, and this relationship here also kind of clues us in to the fact that A times B does not equal B times A, right? Because the order of operations is different. It's that dot product. We're taking the rows of A times the columns of B in this one, and in here we're taking the rows of B times the columns of A. So unless you have a special kind of matrix like a diagonal matrix or a symmetric matrix or something like that, in general this is not going to be the case. Now there is one special matrix for which this will be the case, and that is a matrix which we call the identity matrix. So the identity matrix, we usually call that I. Sometimes you'll see it with the number 1, but normally I use I. So I should have 2 lines there for a matrix. So this is a matrix with all zeros except for on the diagonal. Right? So we have 1s along the top left, center, and bottom right, and then we have zeros elsewhere. And it turns out this matrix, if you multiply it by any vector, you just get that same vector back. And if you multiply it by any other matrix, you get that same matrix back, no matter what the order is. So if you have A times I, that's the same as I times A, which is just A. That's the one special case where this holds. For a general matrix B, A times B will not equal B times A, but for the identity, A times identity is equal to the identity times A, because it's just A in both cases. So the identity is like 1 for scalars. Multiply any scalar by 1, any number by 1, you'll just get that number. Multiply any matrix or vector by the identity, you get that, and then you get that matrix or vector back. All right, so that's a very basic introduction to matrices and vectors and how we work with them. So I'll see you in the next videos.